Okay, everyone, we are going to take a look at Lewis dot diagrams. But before we get too far into Lewis dot diagrams, we're going to review some things about naming and making formulas for covalent molecules because we're going to need that as we go into Lewis dot diagrams. So, covalent naming. I got three molecules for you here, CO2, CO, and N2O3. Now, the names for these, I'm going to give them to you and then we're going to talk about them. CO2 is carbon dioxide, CO is carbon monoxide, and N2O3 is dinitrogen trioxide. So, looking at these names, we're looking at the first element. So, let's start with the C's. Notice that there is no subscript on them. It's just C. That means that there's only one carbon in each of these. So we do not put a prefix on this one. Okay. If there's only one atom, then there's no prefix. However, with like the nitrogen here in the N2O3, it gets a prefix, the dinitrogen, because there are two of them. When we're looking at the second element, first let's see that all of the endings are IDE. So we change the ending to "ide," kind of like we did in ionic bonding. For the prefixes, we have tri, di, and mono here. And that tells us what the subscript is on those oxygens. We always put a prefix for the second word. No matter if it's 1, 2, 3, or 10. We put a prefix there for the second word. The prefix tells you what the subscript is. If there's no prefix, then there's no subscript. That means we only have one atom. So we can go from name to formula as well. We see dinitrogen trioxide. So dinitrogen means we have two nitrogens. Trioxide means we have three oxygens. So we get N2O3. We do not have a prefix on this sulfur, which means that there's only one of them. Hexa as a prefix is 6, so that means that we have 6 fluorines. So we get SF6. Okay, Lewis structures or Lewis dot diagrams. We'll use those two words interchangeably. Lewis dot diagrams help us to visualize how covalently bonded molecules are organized. The dots represent valence electrons. Now that word valence, it's a fancy word meaning outer electrons. So if you think back to when we were learning about the structure of an atom, the electrons in the outermost energy level are the ones we're talking about here. Almost every element can have 8 outer electrons, except hydrogen and helium, which can only have 2. Okay, now this doesn't mean they do have 8. It means they have the potential to have 8. And we're trying to get up to 8 in order to be happy, be fully satisfied, we could say. Again, with the exception of hydrogen and helium, which are only trying to get to 2. Now, when we're looking at a Lewis dot structure, the dots each represent one valence electron or one outer electron that is not bonded. That means it is not shared with any other element. It is that element and that element's only. So if we see 2 dots, that atom has 2 non-bonded electrons. When we see a line, that means that it is 2 valence electrons that are bonded or are shared between 2 different atoms. So we can start by looking at Lewis structures for single atoms. Now these are not going to be bonded, so we're not going to see any lines. We're only going to have the dots. So the dots are placed around the element symbol one at a time, and then they will pair up. We're going to think of our element symbol as if it's in an imaginary square. Okay, so that means we have 4 sides with which to place our valence electrons. So when we have carbon, carbon has 4 valence electrons, 4 outer electrons. So I'm going to put 1 dot on each side. Fluorine has 7 valence electrons, so I'm going to put 1 dot on each side and then go back and double up 3 of the sides. Now, why am I being so particular about where you put them? The placement of these helps you to determine how many bonds is this potentially going to form. So the number of spots with only 1 dot or 1 electron indicates how many bonds that atom can form. So carbon here has 4 spots with only 1 dot, which means it can form 4 bonds. Fluorine has 1 spot with 1 dot, which means it's only going to form 1 bond. Okay, let's get into some bonding here. Covalent bonding in H2. So I have 2 hydrogen atoms. Each of them have 1 electron. So I've got my H with 1 dot, and I got my H with 1 dot. Now remember, hydrogen wants to have 2 valence electrons in order to be happy. So if these 2 got together and they shared these 2 electrons that they have, they are going to form a covalent bond. So we put those 2 dots then in between, and we can turn them into a line to show that they are shared. This makes each of those hydrogens have the electron configuration the same as helium. So when we're counting electrons now here, we're counting electrons here now. This hydrogen on the left has the 2, and this hydrogen on the right has the 2, even though they're shared. Okay, think of it like when you share with someone, you can say, yeah, I have a Chromebook, even though you might be sharing it with someone else. You can each say, we have that Chromebook. So let's look at another example, covalent bonding in F2. We have 2 fluorine atoms. We had drawn these before, so we got 7 valence electrons around each of them. We got the potential for 1 bond here with each of them. They're going to share these 2 valence electrons to form that covalent bond. Okay, now we can turn these 2 into a line, and that means that this fluorine on the left has 8 around it, and the fluorine on the right has 8 around it. So that sharing causes each of their pairs to have the same electron configuration as neon. Now, how do we do a Lewis dot diagram? I'm going to go through these steps, and then we're going to look at it a little more closely with an example. So bear with me here as we go through the steps. First thing we need to do is make certain that the bond is covalent. Once we know that, we're going to add up all of the valence electrons for all the molecules, or all the atoms in that molecule. So if we have 4 carbons, we're going to do 4 valence electrons times those 4 carbons, add them all up. Then we're going to create a skeleton structure. We're going to figure out which atom is in the middle and which are on the surrounding sides. Now, the least electronegative element is going to be in the middle. We don't have to look up the electronegativity every time we want to figure this out. We're going to know that hydrogen never goes in the middle. Carbon is typically in the middle. It's typically the first element in the formula, and it's typically the element with the least valence electrons. We're going to place single bonds between the middle element and whatever elements you decided were on the outer. Now, if you're having trouble figuring out which is the middle and the outer still, know that the group 17, so fluorine, chlorine, bromine, iodine, are typically surrounding elements. They rarely go in the middle as well. For each single bond that you place, so each line that you drew, you're going to subtract 2 from that total valence electrons that you found in step 2. Okay, so if I placed 4 bonds, 4 lines, then I'm going to subtract 8. Then you're going to check, how many electrons do I need to fulfill all of the octets, so put 8 electrons around every single atom, if I put in dots. Okay, now if you don't have enough, that's when you're going to go back and double or triple bond. If you do have enough, then you're just going to put in the dots and you're done. Okay, that's probably pretty confusing, so let's take a look at an example. If we have CF4, okay, CF4, sum up all the valence electrons. We've got 4 electrons coming from carbon, and we have 7 electrons coming from each of our fluorines for a total of 28 coming from fluorine. That gives us a complete total of 32 electrons. We're going to complete the octets on the surrounding atoms after we've drawn our skeletal structure. So let's start with the skeleton structure. We put carbon in the middle, we put the 4 fluorines around it, and we draw the bonds in. Okay, now I used 2, 4, 6, 8 electrons in doing these bonds. Okay, so I have, if I take 32 minus 8, I've got 24 left. Now I'm going to see which ones are happy. My carbon is happy. It's got 2, 4, 6, 8 electrons. How many it wants? Each of these fluorines also wants 8, but right now they only have 2 coming from this shared bond. So I need 6 more there, 6 more here, 6 more here, 6 more here, for a total of 24 more. Now, remember how many I had left? I had 24, so I can simply put in my dots. Okay, I put 6 dots around each of the fluorines, and I have 8 electrons now around each of these fluorines, and I've used all of those electrons that I had to start with. Okay, so I place the leftover electrons on the central atom and then around the outside. And then if necessary, I would have done multiple bonds to fill the center atom's octet, either double or triple bonds. Now some vocabulary. Remember that the bond line is equal to 2 valence electrons. These dots on the outside are called lone pairs. When we have double and triple bonds, that means that more electrons need to be shared in order to fulfill octets. So if we have this carbon dioxide, we can change these dots into lines. Now that means that this oxygen has 2 electrons coming from this line, 2 electrons coming from this line, 2 from these dots, and 2 from these dots, okay, for a total of 8. This carbon has 2, 4, 6, 8, 2 from each of the lines. And again, that oxygen is the same as this oxygen over here. When we look at hydrogen cyanide, we have the H only needs 2, so it's only got 1 line. The carbon needs 8, so it's got 2, 4, 6, 8 from those 4 lines. And then this nitrogen has 2, 4, 6 from the bonds and 2 from this lone pair. Okay? Okay, let's go through one last example. We've got N2. So N has 2 of them. There are 2 N's. Each of those have 5 valence electrons. So I got a total of 10 electrons to work with. Okay, now we don't really have a skeletal structure here because we don't have a center atom. So I'm going to put my 2 N's next to each other and bond them. I had 10 electrons. I take away 2 for this one bond and I get 8 remaining. Okay. If I were to put in 8 dots here, this nitrogen would have 6 electrons, this nitrogen would have 6 electrons, which is not enough. So I'm going to go and I'm going to double bond. Now, with my bonds, I've used 4 electrons. So I had 8 left over here after my single bond. Take away 2 again, I get 6 left. If I put in 6 electrons, this one would have 2, 4, 5, 6, 7. This one would have 7. Okay, not enough. Our goal is 8. So I need to triple bond this. Okay, now I got 6. I had 6 left over before I did my triple bond. I did my triple bond. I now have 4 left over. If I put in 4 dots, we got 1, 2, 4, 6, 8. 1, 2, 4, 6, 8. Perfect. I've fulfilled my 8 electrons. So the correct Lewis structure has all of the electrons used. Right? I used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is what I had. And all of my atoms have 8 valence electrons. Okay, last thing here. I want you to pause the video. I want you to write out the Lewis dot structure for just Si, for NF3, and for C2H4. Okay, pause it, do your thing, try them out, and then I'm going to show you these answers here in a second. So if you haven't paused it yet, do that. Okay, here are the answers. Si has 4 valence electrons, so it looks very similar to that carbon. We got Si, we got a dot on each side. NF3, we have our N, 3 Fs, they are all single bonded. We use up all of our electrons by putting dots around it. Notice that that center atom can have dots on it. It doesn't have to only have bonds. C2H4. Now, this one's kind of tricky. The carbons are going to be your center, but there's going to be 2 of them. Okay? And when we do that, we end up with carbon needing to be double bonded to the other carbon, and then the hydrogens being single bonded. Okay, now if you got different answers here, make sure you go back and you try them out again, because something probably went wrong in that process, and we want to make sure we get them all right. If you have questions, make sure you let your teacher know. Otherwise, move on to the next assignment.